Welcome to lesson 6.8, regular polygons. So to begin with, we already know what polygons are, but we need to establish what the word regular means in geometry. So the definition of a regular polygon is a convex polygon whose angles are all congruent and whose sides are all congruent. So in order to be a regular polygon, the polygon first needs to be convex, then it needs to be equiangular, meaning all the angles are congruent, and equilateral, all the sides are congruent. So a regular n-gon is how we would name any polygon with n number of sides. So we could call this a regular three-gon or a regular triangle, but it also has a special name in this case because this triangle would also be equilateral and equiangular. The square you see here is a regular four-gon. This is a regular pentagon, a regular hexagon, but we could always also name it by its number of sides. And then again, refresher that equilateral is a polygon that has all the sides being the same length or congruent, and equiangular means all the angles have the same measure. So an equilateral pentagon could look like this. So you'll see it's not regular, but it is equilateral. And an equiangular hexagon would look like this. So it's equiangular, but not equilateral. If you have both of these, then it is a regular polygon. So example 1 says at the center of a diamond is a regular octagon. Find the measure of each interior angle of the octagon. So if you remember, the interior angles formula is to take the number of sides minus 2 and multiply by 180. So 8 sides to an octagon minus 2 is 6. 6 times 180 is 1080 degrees. So we know the interior angles of an octagon add up to 1080 degrees. Octagons have 8 angles, and because it's regular, they're all congruent. So the 1080 degrees divided by the 8 will give us each angle measure, which is 135 degrees. So another vocab term, the center of a regular polygon. Every regular polygon can be inscribed in a circle, meaning all the vertices of the polygon would touch on the circle. The center of this circle, which contains all the vertices of the regular polygon, is also the center of the polygon. So when you inscribe a regular polygon in a circle, the center point of that circle is also the center of the polygon. So then we have the center of a regular polygon theorem, which reads for any regular polygon, there is a unique point, its center, that is equidistant from all the vertices. So the center point of a regular polygon is the same distance from all the vertices. A polygon is inscribed in a circle if all the vertices lie on the circle, so every regular polygon can be inscribed in a circle. So again, refresher on what it means to be inscribed. All the vertices lie on the circle. So example 2 here says RUNLOV at the right is a regular hexagon. Find the measure of each angle. So for part A, they want us to find the measure of angle OEN. So OEN would be this angle here, opening down with the vertice at E. So when we look at that, we know to begin with, I have a hexagon. So a hexagon's total angles 6 minus 2 times 180 is 720. So then if I take that 720 divided by the 6 angles, each interior angle of the hexagon is 120 degrees. So for example, angle RVO here, 120. Angle VOL, 120, and so on around the hexagon. So now we're going to start to break down for OEN and ENL's measures. So for OEN, what we want to look at is angle OEN would be 1/3 of our whole circle. If we think OEN is a center angle of the circle, and its measure, if I look at what it creates, that's 1/3 of my whole circle, because OER would be 1/3 and REN would be 1/3. So 360 divided by 3 is 120 degrees. So that's one way we could find the measure of OEN. Another way is we could find angle OEL plus angle LEN to give us angle OEN. And in that case, we know OEL and LEN are both 60 degrees. So that means OEN is 120 degrees. And I know these are each 60 degrees because if I look at the triangle here, triangle OLE and triangle LEN, these are both equilateral triangles. So each angle measure would be 60 degrees. Then for part B, angle ENL. So ENL, this angle right here, and we know triangle ENL is equilateral because E to N would be the same distance as E to L, and then L to N is that same exact measure because all sides around my hexagon are the same length. So in that case, that's an equilateral triangle. So each measure is 60 degrees, meaning angle ENL is 60 degrees. Then we have the regular polygon rotation symmetry theorem. So we looked at rotation symmetry in a previous lesson. Now we have a theorem to go with it for regular polygons, which states a regular n-gon has n-fold rotation symmetry. So a regular hexagon would have 6-fold rotation symmetry. A regular 12-gon would have 12-fold rotation symmetry. So this theorem enables regular n-gons to be drawn quite easily. So the way that they're recommending that you can draw a regular polygon using this theorem is first, draw a circle. Then you choose any point on that circle, and you're going to rotate it 360 divided by n. So your n-fold symmetry divided by n. So if it's 8 sides, we would want to divide by 8. So you're rotating it 360 divided by n degrees about the center of the circle. Repeat this process n minus 1 times and then connect the points. So you'll see here, I did an octagon, not a hexagon. So you can construct a regular hexagon after you try this octagon approach. So the first thing you do is draw a circle. Make it large enough that you can construct a figure inside, doesn't need to be huge. We know a regular octagon is 8 sides, so that means I'll be plotting 7 more points after I choose my first one to place. And 360 divided by 8 tells me each rotation is 45 degrees. So if I start with putting a point here on top, about the center, so I'd place my protractor at the center, from here measure 45 degrees, and there's the next point of the octagon. Then from that one, protractor at the center, 0 here, measure 45 degrees, there's your next point. You repeat that for all your other points, and then you just go in and draw the green segments here that I have from one point to the next with a straight edge, one point to the next, and so on, till you connect them all, and then you have your regular octagon. So if you'd like to give that process a try, the 3 steps here, I'd construct a regular hexagon here. Then you have the regular polygon reflection symmetry theorem. And the regular polygon reflection symmetry theorem has 2 parts. The first part says that every regular polygon has reflection symmetry about each line containing its center and a vertex. So any line from the center point to the vertex would be a line of symmetry. And then it also has each perpendicular bisector of its sides. So if I did the perpendicular bisector of the sides through the center, that is also a line of symmetry. So you'll see I didn't draw the final one here, but a couple examples here and here, your perpendicular bisectors of each side are lines of symmetry, along with any line from the center point to a vertex. So there could be an extra one drawn here and an extra line of symmetry drawn here. So when a regular n-gon has an odd number of sides, the perpendicular bisector of one side contains a vertex on the opposite side. When n is even, so when we have an even number of sides, each symmetry line either bisects 2 opposite angles, like you can see here, opposite angles, of the n-gon, or it's the perpendicular bisector of 2 opposite sides. Thus, every regular n-gon has n lines of symmetry. So if we have a regular hexagon would have 6 lines of symmetry. So how many lines of symmetry are there in a regular 75 gon? Simply put, use this final line. There are 75 lines of symmetry. If it's a regular 30 gon, 30 lines of symmetry. So practice problems, page 361, 362, numbers 1 to 25 odds.